So, welcome back. As one of the last lectures in the class 11 course, penultimate, okay, maybe, I'm going to talk to you about beautiful phenomenon of beats. Okay, my heart beats. Okay, the drums beat. Okay, that arises due to the interference of waves of nearly equal frequencies. Nearly equal frequencies. The difference of the two frequencies, okay, is normally not more than 10. And I will tell you the reason for that. So the beat frequency is the difference of the two frequencies, nu1 and nu2, and it is less than equal to 10 hertz or cycles per second. Actually, what happens in the phenomenon of beats, that the sounds which come to our ears, they wax and wane, wax and wane. Okay, so there is waxing and waning, just like in the case of the moon waxing and moon waning when you look at the moon. Okay, there are two frequencies, omega 1 minus omega 2 is equal to 2 omega b is equal to 2 pi, the difference of the two frequencies, and this is what we call 2 pi into nu beat. So frequency of the beat is very small, is equal to the difference of the two frequencies. Normally, as I told you, 10 hertz. Okay. Why so? Let me tell you that our ear is able to decipher between two syllables if the interval between the two syllables is not less than 100 microseconds, 100 microseconds, 100 microseconds. Sorry, not microsecond but milliseconds. Okay, so in 1 second, how many different syllables we can speak? That syllable is 10. So therefore, because to understand this phenomenon of beats, normally the beat phenomenon is used by our musician friends to tune their instruments. In fact, to fine tune their instruments. Suppose there is a standard instrument and there is the one which has to be corrected and made up to the mark. Then, you know, in the case of string instruments, what is done is that we tighten the string so that the tension comes to the value that the velocity of waves in that way for sitars and guitars and other instruments like that. Also in the case of tabla, you fix the boundaries and pull at the various strings which are there so that it may come to the tune. What happens to our poor musician friends are those who deal in instruments, who they have trained their ears to listen to what we call the beats. Maybe 10 beats, 9 beats, 6 beats, anybody can listen to. But when it comes to 1 beat or half a beat or a quarter beat, and we don't want any beat, so your ears should be very well trained. Okay, and this is what happens with musicians and the instrument makers. Okay. Let's talk about further the mathematics of it. It's very simple. Because we are talking about this thing. So one more thing. The frequency with which these waves are propagated is equal to omega 1 plus omega 2 by 2, which is approximately equal to, because they are nearly equal to each other, the value is approximately equal to omega and r, approximately equal to omega t. Okay, like if the frequency is of one is 102 and the other is 100, then this frequency will turn out to be equal to 101 hertz. Okay, which is very close to the frequency of the original waves. Now, I can write an equation of kind S is equal to x comma t. I am not writing y is equal to x comma t because I am dealing in longitudinal waves. I can write the waves as a cos of kx cos of omega t. And for the sake of simplicity, I put the value of cos of kx equal to 1, which is that we are dealing it at x is equal to 0, etc. Because cos of 0 is equal to 1. In which case, in general, S will be equal to a cos of omega t. Of course, we take omega 1 slightly greater than omega 2. So I can write using this that S, the resultant of S1 plus S2, which have frequencies omega 1 omega t, can be written as a cos of omega 1 t plus a cos of omega 2 t, which turns out to be equal to, I take the a as common, so I have the relation a cos of omega 1 t plus cos of omega 2 t. Now there is the trigonometrical identity. Okay, cos of a plus cos of b is equal to 2 cos of a minus b by 2 cos of a plus b by 2. Okay. So using this identity, what I obtained is the value of the disturbance S has got two very interesting things. 2a cos of omega 1 minus omega 2 by 2 t and cos of omega 1 plus omega 2. This value is very small and this value is large enough. Okay, I can write this omega b equal to omega 1 minus omega 2 by t 2 and omega a as omega 1 plus omega 2 divided by 2. So I write the equation as 2a like this. Okay. So let us see. This is a traveling wave with the frequency omega a, angular frequency is given by omega 1 plus omega 2 by 2. And this is I have shown it here. This is the amplitude which is time dependent, which is sinusoid. Okay. So the resultant wave oscillates with an amplitude 2a cos of omega t, omega b into t. Okay. Now 2 omega b, this is equal to omega 1 minus omega t, and this is the beat frequency. Okay, this is due to the beat frequency. So I can find that the nu of the beat is equal to nu 1 minus nu 2. How do we detect them? Not with the help of instruments usually, but with your ears. And there are people who can tune a certain instrument to a standard instrument within a matter of a few minutes time. Okay. Our ears, they detect, and our ears have the prowess to detect up to 10 hertz. After 10 hertz, If the difference is more than 10, then we need some other detection instrument. So detection is done like that. Now, normally they tune to some swara, just like swara bhaskar, swara. And in music we have swara. I'll just sing before you. Very bad. Sa re ga ma pa dha ni sa and sandha pa magaris. So one of these is standard. For example, you can do it to dha, or for example you can do it to ni, or what we have, I don't know much about it. When you read, you begin with ABC. When you sing, you begin with do re mi. Do a deer, a female deer, re a drop of golden sun. Me a name I call myself, far a long way to run. So these are also, they are similar to our sa re ga ma pa dha ni sa. So that is what is done in the detection process, and we have beautiful phenomenon of beats and of course our heart beats. And friends, on this side there is a projection of the waves having a frequency of 11 Hertz, 9 Hertz, and then they overlap and give you beat frequency, and that is 2 Hertz. You can look into the diagram and you can look into the similar diagrams, okay, search for them and you can learn more about this. Now we go next to Doppler's effect. So next we take the last topic in our discussion of waves, and that is Doppler's effect. No. This beautiful, lovely effect is not called Doppler's effect. It's so established that we rather call it Doppler effect. No, Doppler. It's Christian Doppler, an Austrian physicist, 1842. Okay, he came out with the proposals regarding the effect known by his name, Doppler effect. Austria is very close to Germany, so much so that Austrians speak German. Well, it was tested in 1845 vigorously by a guy, a person whose name was very interesting, Bose ballot. Like in the Indian system, we buy ballots, okay, by giving money and other perks to people, etc., etc. His name is Bose ballot, okay. Austrian and German. Incidentally, I have two daughters-in-laws, one from Austria and the other from Germany. They both speak German, and I told you the best wives are from Germany. So my next generation has been careful to choose wives from there, okay. Some people are not very happy about it. Anyway, doesn't matter. So Doppler, he proposed an effect which is equally applicable to sound, which needs material media for its propagation, strings, air, which may be dry or wet, whatever, And the electromagnetic waves, we will not talk about that, which consists of the light. Light means electromagnetic waves having a certain range of wavelength between a band of wavelength which is known as the visible band, or a band of frequency which is known as the visible frequencies. Beyond on the two sides, one side is the infrared, less than the visible frequencies, and the other side is ultraviolet. Okay. Before I tell you the phenomenon, because I have just talked to you about the optical systems, then you know that there are the 7 colors: violet, indigo, blue, green, yellow, orange and red. Okay. On this side, on the violet side, high frequency, low lambda, low wavelength. This side, it's otherwise. This is the prominent color, blue, and this is not as prominent. The frequency associated with the blue is more, the frequency associated with the red is less. So, in light, if the Doppler effect is applied, which was applied later on, we find two words. One is the red shift and the other is the blue shift. It doesn't mean that the shift is towards the red color or the shift is towards the blue color. If there is increased frequency, apparently the frequency increases, in this case, then it is known as the blue shift. If it decreases, then it is called red shift. Okay. Now, let me tell you, you are here on a railway platform. That is one of the things which is used to explain. And on these two rail lines, there is a whistling train which is passing your location from left to right. What is observed that when the train is approaching the observer, then the frequency is different. As soon as the whistling object, normally it is with the engine, and it passes this way and it starts moving away from it, then the frequency drops. Okay, so this is what was observed. And you'll say, what happens if the train is not whistling? No. The train on the rails will make some sound. There will be some frequency associated with that. That comes to our ears. Our ears can respond to frequencies which are lowest value of the frequency that the ear can respond is 20 hertz, and the maximum is 20,000 hertz. Okay. So in between the whistling frequency is there also the car of the rail, that also has a frequency which lies in between. And it's very easy for you, friends, to observe that there is a change in the frequency. So there is an actual frequency of the whistle, of the source, okay, and there is an observed frequency. Observed frequency can be greater than the frequency of the source, can be equal to the frequency of the source, can be smaller than the frequency of the source. These are three situations which arise. So, what we do is, we study, for example, if I have a source here, and there is an observer here, in the same line joining the two of them. In the first instance, the source is moving, and the observer is stationary. Okay, ARY, stationary. It is there. It's not moving at all. So what happens? There are two cases. The speed of the source is towards the observer or it is away from the observer. That needs separate treatment. In the second instance, the source is stationary. It's not moving at all. But the observer is moving towards the source. Okay. Or it is moving away from the source. So these are two separate set of mathematical treatment that's desired. In the third case, both are active. Source is also moving towards or away the observer, and the observer is also moving away or towards the source. So both of them are moving, both of them are mobile, and they have a different mathematical treatment. And we can find, if we give the frequency nu, as I said here, this is the actual frequency, then the frequencies that we obtain are calculated. Well, that is interesting. But I leave you here. And I also expect that you may come prepared, okay, for these cases which may happen together. Well, there is one case you must be thinking as to what is the situation that the apparent frequency is equal to the actual frequency. Okay. Now, suppose you are in a train. You are an observer. You have the beauty of observing. And there is another person who is playing on a guitar, a sitar, or any. So now you are sitting in a train, and there is somebody who is playing a guitar at a constant frequency, maybe 256 hertz or more, doesn't matter, any frequency which is fixed. That is the source, and you are the observer. Relative to each other, you are not moving. You are in the same train, you are in the same bus, you are in the same ship, but the ship is moving on the waters. The train is compartment is moving on the rails, and the bus is plying on the roads. So both of you have the same speed in the same direction. So apparently there is no relative speed. So this means that relative speeds also matter, and when the relative speed between the source and the observer is equal to 0, then the apparent frequency which we perceive is equal to the produced frequency which the source is producing. This is basically a kind of qualitative analysis and utterance about the effect given by Mr. Christian Doppler, Austrian, remember. My Badi Bahu is from Austria and the Choti Bahu is from England. And in between there is a son, there is a nephew who is not married. So I don't know where from he's going to get his bride. But I told you that in this land of Austria, and people say, I have no experience. I have a wife from India, decent wife. Okay, so anyway, so look here, and I never told you which countries the husbands are good, okay, because we always say the husbands are difficult beings. Anyway, so what is left for us is to talk about these three categories categorically, okay, and with some examples we will see as to what happens in this situation. Mr. Doppler, whose effect is so strong that we don't call it Doppler's effect, we call it Doppler effect. 1842, long time no see, and was tested by Bose Memorial, who established all observations with regard to sound for Mr. This is actually this comprises of also the sounds of echo. Okay, so let us see what are the, just to wind up this thing, what are the various applications. Sonography, okay, which can be used in many situations in the deep seas and also on the surface of the earth. Well, echocardiogram, okay, and there are several military civilian applications. Okay, I don't like guns, I don't like military actions, I want people to live in peace with each other. So anyway, but the military is there, their actions are there, and they want to be better than their apparent or chosen enemies, etc. Well, there is another item, and that is astrophysics, wherein we use it to determine the speed of stars, the velocity of stars. Okay, so there are many applications of Doppler effect. Okay, Doppler sonography is also there. Okay, what we call it we use the sound waves and ultrasound waves and other things, and everywhere there is an application of Doppler effect. So I leave you there. I've taken a lot of time, and in this the penultimate lecture for class 11th, and I will be done with class 11th courses in the next lecture when I talk about these three situations for the Doppler effect, make calculations and tell you about more, and say adieu class 11th, and I go to the charges and their tahalka. Okay, that is class 12 course. Bye for now. Thank you very much.